everybody. We're about 3 minutes early, but I figured I'd get started. Please say hi and make sure the sound and picture and everything are showing up. Who do we got? Able to hear me all right? Sound is wobbly. Is that better? I move the mic away from me. How's that? Wobbly sound. Did I fix it? Better? No, not better. Okay, not really. How's that? Is that any better? Nope, still not better. Okay, is that any better? Now I'm not using the headphone microphone. Does that work? Do we lose some of the static? The pitch of my voice changes weirdly. Yeah, better. Cool. Yes, kinda. We'll take it. Hey, and it's 7 o'clock. And we got 5 people. 6. What I'm thinking with 50 questions in front of us was that our time might be better served. I was thinking going like 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. That way we'll at least work through a lot of the topics, even though we won't get to every problem. If we have time after those 10, I'm happy to do more. If you guys have questions that come up besides what I'm covering in those 10, please ask me, or if you need me to go more in depth or anything like that, let me know. Does that seem like a solid plan to you, 7? Do every 5? Cool. Samantha likes it. So I'm going to start with number 5. Use the graph to find the intervals on which the function is increasing, decreasing, or constant. Okay, well, I can start and see that the graph is never constant. That was easy. Now I need to know, where is it increasing and where is it decreasing? Okay, so I'm going to say it's increasing. That means going up from left to right. right on that stretch. And then it's decreasing on that stretch and that stretch. Decreasing means going down from left to right. Okay, so find the intervals. Increasing on the interval from negative pi over 2 to pi over 2. So from here to there. Where is it decreasing? It's decreasing from negative pi to negative pi over 2 on that stretch. And then it's also decreasing, union, also, from pi over 2 to pi. That stretch. Cool? Any questions? Pretty easy. Something we did, I think, way back in chapter 2. And then again in chapter 5. Things we should know kind of on top of this, the problem didn't ask about, but when we change from increasing to decreasing, that's a minimum point when we change from decreasing to increasing. And when we change from increasing to decreasing, there's a maximum. Easy. Agreed, Ben. Let's move on. Cool. Number 10. Number 8, 9, and here we go, 10. Graph the function by starting with the graph of the basic function and then using the techniques of shifting, compressing, stretching, and or reflecting. Okay, so we're graphing via transformations. So I'm going to start with the most basic function. The basic function here is, or parent function would be y equals x squared. So I'm going to graph a nice parabola. A little uneven there. Go up the same amount on that side. There we go. Cool. So then the first thing that I see happening is that we change from just x squared. We're going to do this minus 6 part. So minus 6 means that when I plug in an x value that is 6 larger, I get the exact same output that I would otherwise. So I'm going to say, okay, let's make a copy of y equals x squared. There's my copy. And detach it. And then let's bring it over 1 step, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps. Cool. So if that was y equals x squared, that wasn't a very nice squared, then this is y equals x minus 6 squared. And this was a translation by the vector 6, 0, which is the thing that you need to know in our class. Then what? Oh, now I see this negative sign. That's the next thing that's happening. So a negative out in front of the function is a reflection about the x-axis. So I'm going to again make a copy, and then I'm going to reflect that copy around the x-axis. Again, detach it. And now, well, my iPad doesn't have a reflection tool, so I'm literally actually going to rotate it. But pretend I just reflected it. Look how it reflected. Cool, there it is. It's reflected. And now it is y equals negative x minus 6 squared. And that was a reflection about x-axis. Cool. And last step here, we got a +2. So I'm going to, again, make a copy. And I'm going to, again, detach it. And I'm going to move my copy up 1 space, up 2 spaces. So that this is now at the point 2. And I'm now looking at the graph of y equals negative x minus 6 squared plus 2. And you should know that we did a translation by vector 0, 2. Cool. Kind of additional understanding that I'd like us to see here. I'd like us to be able to decompose these into multiple functions. That was something we practiced. So I'd like you to know that if you had a basic parent function, I'm going to call it a of x equal to x squared. Then the first transformation would happen when we did b of x equals a of x minus 6. And then the next piece that happened here was we had c of x equal to negative b of x. And we had d of x equal to c of x plus 2. Right? You should be able to see that as a series of transformations of functions represented by actions that we can take upon separate steps in functions. So we should be able to connect these movements of graphs to these new equations via these geometric transformational descriptions and connect all of that to compositions of functions, right? Like a of x minus 6 or negative b of x. Or posed even another way, because we're having so much fun now, we might even say that if we had a of x equals x minus 6, and b of x equals x squared, and c of x equals negative x, and d of x equals x plus 2, then f of x equals d of c of b of a of x. It doesn't sound fun, Richard. In what possible way is that not fun? It's clearly extraordinarily fun. I mean, it's your final exam in pre-calculus. It's going to be fun. Yeah, you're on it, Richard. And I want you to be able to think about that what is happening question from multiple perspectives. From a graphic perspective, from a transformational perspective, from a function composition perspective. All of those should be ways that you can connect with some fluency. Cool. So seeing no further questions, I'm going to move on to number 15. 13, 14, 15. What are we supposed to do here? Just graph the function. Sweet. 14 and 15. Graph the function. Well, we can do that. No problemo. Cool. What do we got? We got a series of steps for thinking about this function. So let's see. Let's look at domain. Our domain on number 15 should be, we know that x squared minus 3 cannot equal 0. So we know x squared cannot equal 3. So we know x cannot equal plus or minus root 3. So the square root of 3 is what, like 1.7-ish? $1.73. Cool. So I know I've got an asymptote at positive 1.73. No, Richard, I'm doing every fifth problem. Yeah, thank you, Jasmine. And then another one. Oops, that's x equals root 3. And negative root 3. Richard and other folks who have joined us a little later, the reason I'm doing that is so I can cover material from throughout the whole semester, and we don't just get bogged down in only one chapter. But if I finish in a reasonable amount of time with the every fifth problem, then I'm happy to go back and do anything you want to see that I've missed. As you hopefully all realize, there is an answer key attached, so you can all check your work to all the problems regardless. Okay, I got a domain and I got some vertical asymptotes, which I know came from the denominator. Let's see, what am I going to think about next? I think probably next I'm going to look at the zeros of the numerator and think about, do I have any zeros of this function? So I'm going to say we got x squared minus 6x plus 9. Does that ever equal 0? Well, I think that's the same as saying x minus 3 times x minus 3 equals 0. So there's a 0 of the numerator when x equals 3. So I know that the point 3, 0 must be on this graph. So I've got a y-intercept at 3, 0. And I'm going to be graphing in blue here. Bam, 3, 0. Okay. And now I kind of also want to know what happens if I plug in 0. What's my y-intercept? That's my x-intercept right there. X-intercept. This is a vertical asymptote. And let's see. Plug in 0. Let's say f of 0 equals x squared. This was where will f of x equal 0? X squared minus, so 0 squared minus 6 times 0 plus 9 over 0 squared minus 3. 0 squared is 0, minus 6 times 0 is 0, so I've got 9 over negative 3, which is negative 3. So I've got a y-intercept down here at negative 3. So I had 3, 0, and 0, negative 3. Okay, now I'm wondering about, Richard asks, how much problems are there on Thursday? What I've said so far has been 6 or so on that part 1 without the use of Desmos or graphing utility, and then 4 more for part 2, so 10 overall. But that's just a guesstimate. Richard says, wait, how did you find 0, negative 3? Well, I wanted to know what would happen when I plugged in 0, which is another way of thinking about the y-intercept. So I plugged in 0 for x, f of 0, put a 0 here, said 0 squared minus 6 times 0 plus 9 divided by 0 squared minus 3, which came out to just 9 over negative 3, which was negative 3. So when I plug in 0, I get negative 3, and that's a y-intercept. So you plug in 0 to get the y-intercept. Jasmine, you are welcome, Richard. Okay, last thing I'm interested in getting here before I start to do some actual, what do I want? I want a sign chart. But I'd still like to know about, how about a vertical or a horizontal asymptote? That's a question that still remains to me. Horizontal asymptotes. So something that we learned was that the horizontal asymptote comes from the relationship between the numerator and the denominator. So if you have a numerator with degree less than the denominator, we learned that we always got a horizontal asymptote of y equals 0. Because if the degree of the numerator is less than the degree of denominator, then as we approach infinity, the function also approaches 0 towards negative infinity or positive infinity. Then we said, okay, if the degree of the numerator is the same of the degree of the denominator, well, then the horizontal asymptote comes from the ratio of the leading coefficients of the numerator and denominator, which is the situation we're faced with here. Then we said if the degree of the numerator was 1 more than the degree of the denominator, we were going to get an oblique asymptote or a linear asymptote. And then if the degree of the denominator was more than 1 greater than the degree of the denominator, we would get n behavior that represented some polynomial function, whatever the non-rational polynomial term would be if we did long division. Okay, so we have the same degree of the numerator and the denominator. I can see that there's like a 1x squared here and a 1x squared here. So I'm looking at 1 over 1 equals 1. So we've got a horizontal asymptote at y equals 1. So I'm going to go ahead and sketch that in. Y equals 1. Okay, now I'm finally ready to start looking at a sign chart. So I want to know what are all the critical values of this function, all of the zeros of the numerator and the denominator. And then I'll be able to tell when is this function positive and when is this function negative. Okay, so let's start trying to do that. I'm going to zoom in over here and say zeros of numerator and denominator. Well, we only had 2, which was nice. We had a 0 at negative root 3. We've got one at positive root 3. And we've got a 0 at 3. So I'm going to represent that on a number line. I'm going to say here's negative root 3. Here is positive root 3. And here is 3. And now I want to say what are some representative values in each of those intervals. My first interval will be the interval from negative infinity to negative root 3. And a value here might be like 2, negative 2. Then what's a value on the interval from negative root 3 to root 3? And something there might be like 0. Then I want to know what's a value between root 3 and 3. And something there might be like 2. And then what's a value between 3 and infinity? Maybe 4. And now I'm wondering, for each of these intervals, is the function positive or negative? So my function, again, to reiterate it right here where we can see it, is f of x equal to x squared minus 6x plus 9 over x squared minus 3. And let's zoom back in here to my sign chart. And let's see. F of negative 2 is going to be negative 2 squared, so that's positive, minus 6 times negative 2. So we got 4 plus 12 plus 9. So we're positive on top. And on the bottom, 4 minus 3, positive. Positive right there. Then I want to say, it's an ugly looking arrow. Positive. What happens with f of 0? Well, we had 9 over negative 3. I know my output there is negative, which makes sense because at negative root 3, we have odd multiplicity. So the function should change from positive to negative. Oh, good. Then at root 3, we got, okay, here we have f of 2 in this interval. And f of 2, we've got 4 minus 12. That's negative 8 plus 9. Oh, that's 1, so that's positive. 2 squared is 4 minus 3 is 1. Positive. F of 2 is positive. 12, negative 8. Oh, yeah, cool. I'm on it. Positive. Sweet. Because we again have odd multiplicity at root 3, so we should change from negative to positive. Hey, Brennan's dad. Say hi to your dad for me, Brennan. And then over here, we've got f of 4 and 4 squared minus 6 times 4. We got 16 minus 24. That is negative 8 plus 9 is 1. And on the bottom, we're still positive, which again makes sense because we have even multiplicity at 3. So the function maintains its sign. Richard's dog's cousin says hi. Thank you, Richard's dog's cousin. I appreciate that. Richard, say hi to your dog's cousin for me. Okay, we did a sign chart. We got lots of features of this graph now. I think we are ready to start sketching. So we know lots of things. We know that this function approaches 1 for extraordinarily large values of negative infinity. And Bryce, good to know. Owen says hi. Hi, Owen. Hi, Bryce. Then we're going to approach infinity. We're going to go up here. We know that the function does not go negative, so it's got to go up towards positive infinity as we approach negative root 3. Then we know the function must change sign and be negative over here. And we go up. And somewhere in here we know we got to go back down and go back down towards negative infinity. Sweet. Then we know that the function changes sign, comes up towards positive infinity, and touches that 0 at 3, 0, and goes back out and approaches 1. Totally rad. Okay. Some things you should be able to do on this problem that are not explicitly asked for. We looked at rational functions when we said we could use limits to be really clear and precise about some of the behaviors of the function. So you should be able to express limiting behaviors of the function. You should be able to say things like the limit as x approaches negative infinity of f of x is equal to 1. You should be able to say things like the limit as x approaches negative root 3 from the left side of the function f of x is equal to positive infinity, whereas the limit as x approaches negative root 3 from the right side in f of x is equal to negative infinity. The same thing is true at positive root 3. We could use limits there. And I'll do one more. We should be able to say that the limit as x approaches infinity of f of x is equal to 1. I agree, Richard. It's rad. It's totally rad. So there all was by hand with no Desmos. Certainly we could get some more precision here. Like, I really have no idea whether this maximum is on that side or that side and exactly how high it gets. I just know it doesn't cross the x-axis. I don't know, like, some things kids have wondered, like, how do I know if it doesn't cross this asymptote? I don't really. It might come below the asymptote and then go back up from below. But I know it never hits 0. So we're reasonably good over here. Again, this might cross above the asymptote and then come back down. I'm not really sure about that. Those are all things. So if we had Desmos, we could look and be real nice and precise. But this is a great version by hand. If we want to go over and check on Desmos, we can. We can say, okay, what happens when we graph f of x equal to x squared minus 6x. I'm actually going to put in my x squared minus 3 here. And then up top, we got minus 6x plus 9. And there it is. So there, a little cleaner. So if this is on the graphing utility section, you might have some more information here that you should be able to use effectively. So there's the graph. It does look fairly similar to our graph. We know we've got a bunch of asymptotes we could sketch in here, like x equals negative root 3 and x equals positive root 3. I'm going to change this function to blue like I used, and here to red, and go dashed line, and red with dashed lines, and y equals 1, also purple and dashed lines, just like I did. Cool, there it is. So with or without Desmos, all things you should be able to do. Any questions on 15? My graph is wrong? That's bad. Are you being serious, Richard, or are you just making a joke? Looks fine, right? Yeah, looks great. Oh, cool. Let's do number 20 then. 17, 18, that's page 5. 20. F of g of negative 1. Be able to think about function composition. F of g. Ooh, that's terrible. Of negative 1. So I want to take negative 1. I want to be able to plug that into g of x. It goes into g of x first. Negative 1 goes into g of x, and I can see that the output when we're at negative 1 is right here. This is negative 1, negative 2. So that means I should be able to take that negative 2 and plug it into f of x. So f of x, when I plug in negative 2, gives out 3. Number 20. F of g of negative 1 And the answer key gave you -2 as the answer. That's weird. I totally get 3. Where do they mess up? -1, -2, -2 gives 3. Do they want f times g of -1? I meant to give you a composition question. Maybe I was wrong to do that, and I should have instead given composition. They wanted to multiply. So it looks like they wanted you to multiply here. F times g. So that means we plugged in -1 and got -2. And we plugged in -1 and got 1. And we did 1 times -2, and it told us -2. Okay. Well, that's less exciting. I'm more interested in you being able to compose functions with a graph, but they just asked you to multiply. So this was f of x, well, f of, sorry. F times g of -1, which is the same as f of -1 times g of -1. So we had 2 points that we were looking at. This point was -1 comma -2. And this point was -1 comma 1. So f of -1 was 1. No, f of -1 was -2. And I had it was 1. And g of -1 was -2. So the f times g of -1 was -2. That's number 20. Cool. Any questions about number 20? All right. 25. Find the domain of the composite function f of g. So we should be able to compose functions and then think clearly about their domains. So what is the composite function f composed with g? Well, f composed with g of x, in other words, f of g of x, is equal to, take 5 and plug in g. So we're going to say 5 over, and instead of x, I write g of x, which is root x minus 5 minus 7. So first of all, I'm going to say, what's the domain of g of x? And the domain of g of x is the set of values x such that x is greater than or equal to 5. Okay. And then here, I know that in my composed function, it's not possible for root x minus 5 to be 7, because 7 minus 7 would be 0. And that's a restriction on the domain of this rational function. So I'm going to go over here and I'm going to say, for what values of x does root of x minus 5 minus 7 equals 0? Because that can't be allowed. So root of x minus 5 then can't equal 7. So just x minus 5 can't equal 49. And so x cannot equal 54. Not allowed, not allowed, not allowed, not allowed. So the domain then, my final answer, is that the domain of f of g is the set of values x such that x is greater than or equal to 5 and x is not equal to 54. Because if I plugged in 54, I'd get 54 minus 5, which is 49. Square root of 49 is 7, and 7 minus 7 is 0, and we're not allowed to divide by 0. Cool. There's my domain on number 25. Richard, I will be here after school tomorrow. You're welcome to come in. I don't know if I will be here for a full 2 or 3 hours, but come on in. Uh, 30. Finding the inverse of a function. So here I've got y equals 3 over x plus 7. I'd like to switch x and y to find an inverse. So that means x equals 3 over y plus 7. Now I want to solve this rearranged function for y, and that will be the inverse function. So let's see. How am I going to get y by itself? Well, I'm going to try multiplying by y plus 7 on both sides. Because that cancels over here. So now I have y plus 7 times x equals 3. And then I'm going to divide by x on both sides to get rid of that. So now I have y plus 7 equals 3 over x. And then I'm going to minus 7 on both sides to get rid of that. So now I've got y equals 3 over x minus 7. Cool. Final answer. F inverse of x is equal to 3 over x plus 7. Done and done. Feel good? Feels bad. I just solved that, and that's not what I got. 3 over x minus 7. Whew. That was going to be scary. There we go. Oh, now your answer key has that same function of that I got, but it's written in a different form. So I like my form. The answer key goes on to rearrange that to say that's 3 over x minus 7x over x, which is then 3 minus 7x over x, which is then they write as negative 7x plus 3 over x. I think my way looks nicer, but if you like their way, that's also true. Same as answer key. Thanks, Richard. I have enjoyed having you as a student. 35. Graph the function and its inverse on the same Cartesian plane. Cool. Well, it's nice to be asked to graph log functions with their inverses because you kind of want to find their inverses anyway. So we've got y equals log base 1/8 of x. We're going to switch the x and the y to find the inverse. So that means x equals log base 1/8 of y. And then we're going to say, okay, as we rewrite that into an exponential function, we're going to get y equals x, y equals 1/8 to the x. Okay, now I'm going to say, here is x, and here is f of x. And then, or how about I make a table for f of x, xy. That's a cleaner way to do it. And I'll also make a table for f inverse of x, x, and y. It's frozen. It froze. It froze. I think the screen froze. Can't see what you're doing. That's terrible news. Let us fix that. Okay. I see. I hear. I got you. I'm fixing it. Okay. I see you all. We gotta go here. Switch real quick, and back to there. Aha, we are unfrozen. Unfrozen. So, those of you who did not get to watch me do this, I said if this is f of x equals log base 1/8 of x, we're supposed to find the function and its inverse. So to get the inverse, I said, all right, what we've got is y equals log base 1/8 of x. To find the inverse, I take the x and the y and I switch them, x, y. Then I'm going to solve this function for y, and that will be the inverse function. So here, log base 1/8 of y turns into y equals 1/8 to the x. So here's f of x. Here's its inverse. Richard Descartes, who famously said, cogito ergo sum, or, because he was French, he probably said it as je pense, donc je suis. But we know it best as I think, therefore I am. Also managed to invent the XY plane graphing, whereby he joined algebra and functions with geometry and shapes. And math was way more fun forever after. That's why we call it the Cartesian plane, because Descartes was from Cart, which is what his name means, from Cart, which is a place in France. So we call it Cartesian. He actually invented a number of other things, including a sweet thermometer where the changes in the density of mercury would move little bubbles up and down, and it's called the Cartesian thermometer. Anyway, we were back here. It's nicest to use this function, y equals 1/8 to the x, to choose x and y values, and then we'll also use the same things in our original function, f of x. So I'm going to go over here and say, in this function, 1/8 to the x, what happens if I go to the -2 power, the -1 power, 0, 1, and 2? Well, 1/8 to the -2 is 64, 8 squared. 1/8 to the -1 is 8. 1/8 to the 0 is 1. 1/8 to the first power is 1/8. And 1/8 to the second power is 1/64. Switch them for the original function. So 64, -2, 8, -1, 1, 0, and 1/8, 1, and 1/64, 2. Okay, so over 64, -2, I can't really fit that in. Over 8 down 1, 6, 7, 8 would be right there. There's 8, -1. Over 1, 0 is right there. Over 1/8 up 1. And over 1/64 up 2. Cool. So that function has a vertical asymptote at 0 and travels down like that. Cool. Then on the inverse, we can plot -2 up 64, because that doesn't really fit. -1 up 5, 6, 7, 8. 0, 1, 1, 1/8, and 2, 1/64. So that's a function that goes like that. Cool. We know that functions and their inverses have symmetry about the line y equals x. So just to be cool, we could plot that line in there. We know that the two functions could flip around that function, around that line y equals x, and they would be mirrored onto one another. We know that the domain of one function is going to be the range of the other, and the range of one function will be the domain of the other. So over here, domain is the set of values x such that x equals all reals, as it is for any, oh, sorry, my fault. Domain here is x such that x is greater than 0, because we can't take logs of negatives. And the range over here on the blue function is all reals. Y such that y equals all real numbers. And then on the exponential inverse function, we've got domain such that x equals all reals, and range y such that y must be greater than 0. Things worthy of note here is there's a horizontal asymptote there on the inverse function at y equals 0, and there's also a vertical asymptote there on the original blue function at x equals 0. Anytime we have limiting behaviors like asymptotes, we could use limits to express it. So we could say that the limit as x approaches 0, which it only does from the right on the original function f of x, equals positive infinity. And we could say that the limit as x approaches infinity of its inverse, the red function, equals 0. Cool. Richard says it's easy, which I hope you all agree. If you understand things, then they usually are easy. Onwards to number 40. Okay. The first recorded population of a particular country was 22 million. The population was recorded as 34 million 10 years later. The exponential growth function, a equals 22e to the kt, describes the population of this country t years since the first recording. Use the fact that 10 years later, the population increased by 12 million. That's the difference between 22 and 34. To find k to 3 decimal places. Okay, so we know here that a equals 22e to the kt for a in the population of the country and t equaling years since the first recording. So at t equals 0, a equaled 22 million. Yep, we can see that in the function. Cool. So we got 0, 22. That makes sense. And we also know that 10 years later, we should get 10. And then how much? 34. 12 million higher. So we can say that 34 was equal to 22 times e to the k times 10. So I'm just plugging in that point into the function. Okay, and then I'm going to solve for k. That's what it told me to do, was find k to 3 decimal places. So the first thing I'm going to do if I'm solving for k would be to divide by 22 on both sides. 34 over 22 is what? 17/11ths? 17/11ths equals e to the 10k. And then we can say, rewrite as a log statement. So log base e of 17/11ths equals 10k. Oh, log base e, we know that one. That's the natural log of 17/11ths. And that equals 10k. So k is going to be the natural log of 17/11ths all over 10. So that definitely looks like something you should be able to do without Desmos whatsoever, even though it is kind of a function-based graphic thinking problem. It might be on Desmos or not Desmos. I am going to show on Desmos, just because that's what the screen I have here, how to evaluate that so I can find it to 3 decimal places. So I do ln of 17/11ths, and that's all divided by 10. And I find that k equals 0.044 if I want 3 decimal places. 3. Cool. That was number 40. There we go. You should certainly be able to plug that into your standard scientific calculator by doing ln 17 divided by 11, close parentheses, divided by 10. Sweet. And 45. We're coming to the end of our every fifth problem. Hopefully I'm moving at a reasonable pace and I'm not leaving too many people behind. If you have questions, please do stop me. Sequences defined recursively, write the first 4 terms. Awesome, nice easy problem. A sub 1, it's given, it's 7. To get a sub n, I take the previous term and divide by n plus 1. So a sub 2, I take the previous term, which is 7, and divide by 2 plus 1, so that's 7/3. A sub 3, that's the previous term, 7/3, divided by 3 plus 1, so 7/3 over 4, we're looking at 7/12. Cool. And a sub 4 equal to 7/12 divided by the previous term 4 plus 1, which makes 5. 7/12 divided by 5. 5 times 12 is 60. We're looking at 7/60ths. Cool. There they are. 7/3, 7/12, and 7/60ths. And cool. 50. Very last one. I think it should look familiar because if you rolled a 3 in the summation race, you got this explicit function. And I think I evaluated it in class, in both classes. But this is given by the function a sub 1 over 1 minus r, which in this case equals 4 over 1 minus 2/3, which equals 4 over 1/3, which equals 12. Yeah, that's it. You just add up an infinite number of things and then it equals 12. Not a big deal. As the kids like to say, NBD. Not a big deal. Just infinity. That was it. Did it in an hour. Cool. Anyone got any other questions? Jasmine says, let's look at a piecewise function. That's a great plan. Let's do it. Way back at the beginning. I think we got some piecewise functions in here. Where we got them? Not on the first page. Maybe, oh, here we go. 3 different piecewise functions. You got a preference, Jasmine? 7, 8, or 9? I believe it's 9. You want to do the piecewise word problem? Let's do it. Cool. What is the charge for 200 minutes of calls in 1 month? Well, the charge for 200 minutes of calls, you're going to be paying $20 for that first 100 minutes. So it's $20 plus another 100 minutes of calls at 7.5 cents per minute. And Jasmine R, certainly we can do 8 or 7 after this. Yes. So 100 minutes. Oh, my color coding is annoying. That one is black. That's the black part. And then 100 minutes times 0.07, 7.5 cents, which all adds up to what? 100 at 7.5 cents is $7.50, so $27.50. Is that what you guys get? Number 9. Oh, I lost my answer key to number 9. Hopefully that's right, but you can check the answer key. Cool. What is the charge for 250 minutes of calls in 1 month? Okay, so 250 minutes of calls. Well, we now know that after 200 minutes you pay $27.50, but let's go ahead and do that part again. You're paying the base cost of 20 bucks. You're paying another 100 minutes at a rate of 7.5 cents per minute. Then you're also paying 50 more minutes, 50, at a rate of 10 cents per minute. Cool. And that all adds up to $5 more than $27.50, so $32.50. Agreed. $32.50. Construct a function that relates the monthly charge C for X minutes of calls. So I'm thinking of calling it C of X. And I'm thinking it looks piecewise. And I'm thinking it's got 3 different domain restrictions. Domain restriction number 1, domain restriction number 2, and domain restriction number 3. I'm going to say the first one is if 0 less than or equal to 100 minutes. A couple things to note. I'm saying X could be equal to 0 because I think if you actually just never use minutes but still have a plan, you probably still have to pay the 20 bucks. And then it's saying including 100, so I said here including 100, I said less than or equal to again here for 100. And the cost here for those 0 to 100 minutes is just 20 bucks. Cool. And then the next domain restriction is if we're between 100 less than X less than or equal to 200. Well, now you're going to pay that 20 bucks plus you're going to pay 75 cents for each value of X over 100. No, 7.5 cents. Sorry. Keep doing that. 0.075. Cool. And then in the last section, you're paying, this is for values of X over 200. And here you're paying the $27.50 that we got right here, right? For exactly 200, plus additional costs for every X over 200 of 10 cents. And that's what I get for number 9. You'll notice that in the book, the answer key that I attached, they have kind of simplified that function. I would just do it like this because I think this is like really clear what's happening. But they've actually like distributed the 0.075 to the negative 100 in the X and then added it up with the 20. And they've distributed the 0.1 to the negative 200 and then added that with the 27.50. If you feel like doing that, certainly make it happen. But I like my way better. I think it makes it really visually clear exactly where the pieces came from. Any questions on 9? Cool. And then Jasmine says 8 or 7. Okay, let's do 8. Graph the function, negative x plus 2 for values of x less than 0. Well, sounds good. Negative x plus 2 is a function that goes, oh, they left the scale off the y-axis. How kind of them. I'm going to call that 1, and that's 2, and that's 3, and that's 4. So negative x plus 2, that's this part. I'm going to say does not actually reach 2, so I'm going to put an open circle. See you, Richard. I'd be happy to, Lauren. And then it goes down 1 over 1. So 1 like that and like that. So it's a function going there. So that's the negative x plus 2 part. And then the root x plus 3, we plug in 0, we get 3, and that's a closed-in circle because it actually does equal 0. Then if I plug in 1, square root of 1 is 1, plus 3 is 4. 1, 4. 4, square root of 4 is 2. 2 plus 3 is 5. So 4, 5. And it's a square root function. It looks something like that. That's, let's see. So labeling points, I could say here was negative 2, get 4. Negative 1, get 3. Over here we had 0, and you'll get 3. Plugged in 1, and you'll get 4. We plugged in 4, and you'll get 5. There it is. F of x. Cool. Do you want 8 as well? I mean, I can do 8 really quick, right? Real fast. Piecewise function, f of x equal to, f line goes down 2 over, no, down 1 over 2. X, if x is, we got what? Negative 4 less than or equal to x less than or equal to 0, and then it goes just x if we're between 0 and 3. Bam. Cool. Some piecewise function work. Any questions on any of that? Before I move on to 13 or 17 as per Lauren's request. Doesn't look like it. 13 or 17. 10, 13. Which of the following polynomial functions might have the graph shown in the illustration below? Oh, how fun. Okay, so let's see. I can see that this has to have a 0 here at, that's got to be 1. And that's even at 1. And it's got to have a 0 at 2. And that's got to be odd. And that's got to be odd. And it's got positive, even, and behavior. Okay, so I can say x squared x1, okay, x squared x squared. Okay, so they all have positive and even and behavior, so can check that off. They've all got that. Now this one, so this one is even at 0. That's no good. Even multiplicity at 0, don't want that. Cross out A. This one, also even multiplicity at 0. Same thing here. Get rid of it. No good. Okay, so now I'm coming over here. Both have odd multiplicity at 0. Solid. Now one of these has even multiplicity at 2. I don't want even multiplicity at 2. That's bad. Even at 2. Don't want that. Get rid of that. So it must be D. X times x minus 2 times x minus 1 squared. Here's where my even multiplicity is. Here's odd and odd multiplicity. Check, check. If I was on the Desmos section, I might come over here just to be sure and graph x times x minus 2 minus 1. Oh, didn't close that. X minus 1 squared. And I can see, yes, it does in fact look just like it. Beautiful. I distinguish even and odd multiplicity by saying that 2 is an even number. Even number. Whereas, notice that this one is a 1, and a 1 is an odd number. The even or oddness of the exponent at that 0. Jasmine? So that one was clearly not it because it only had evens. Even. That function would have never dipped below the x-axis. It would have just bounced and bounced and bounced. Cool. What did Lauren ask for, 13 or 17? Should we take a look at 17 as well? 17, ooh, this is another fun one. Kind of the same picture here. Let's see, what can we got here? I got a 0 at, that's -5 and 8. So this counting by 1, 1, 2, 3, 4, 5. Yeah. So 0 at 1, 2. So I need to get 2, 0. I've got a vertical asymptote at x equals -1. 1, 2, 3, and another one at x equals 4. Okay. I know that here, this is even behavior because it's keeping the same sign. And I know that here, that's odd multiplicity because it's changing signs. Okay, so just looking at that, I can say this one, I've got odd and even, odd and even, odd, odd, totally wrong. Okay, so here I have the entirely wrong asymptotes. That's bad, right? So this is clearly not it, dead. Here I have the wrong multiplicity. Wrong multiplicity. The zeros in the denominator. So that's bad. Get rid of that. These both check out, right? Even, even, odd, odd. Both of these give me a 2 in the numerator. So now I'm looking at the difference between this one and this one. Both of them give me zeros at 6. 6, 0. 6, 0. So these two are very much alike, right? X minus 2 squared, x minus 2 squared, x minus 6, x minus 6, x plus 1, x minus 4. Okay, so the only difference between this one and this one is that here I've got a cubic on top and a cubic on the bottom. So this one should have horizontal asymptote at y equals 1 because they're in the ratio of 1 to 1. And this one should have a horizontal asymptote at y equals 2 because this is in a ratio of 2 to 1. Okay, so which one is it? Is it y equals 1 or y equals 2? Well, I think we can look here and we can say pretty clearly there's not a horizontal asymptote at y equals 2. Not the horizontal asymptote. Right? That's clearly not it because it crosses the function right there. Right? That's pretty bad. So I think we can pretty safely assume that this graph is better matched with a function that would have a horizontal asymptote at y equals 1, right? We're approaching y equals 1 on both sides. Horizontal asymptote should be at y equals 1. So that was the only distinguishing characteristic, which is why I say A. Does my answer key I gave you agree with me, or do they? Yeah, they agree. Cool. Any other questions? No? 8:23, time to go home? I can live with that. That sounds good. I will catch you guys on Thursday. There's things that I didn't cover and you'd like me to, come on in tomorrow. Otherwise, I think that was a kind of reasonable overview of some stuff about piecewise, function composition, transformations of functions, rational functions, exponential functions, polynomial functions, kind of the process for asymptotes, a little bit about limits. We did a sequence or a series problem. That was a lot of what we covered this semester. See you all later. You are welcome, Jasmine. You are welcome, Lauren. You are welcome, Michelle. No problem. Have a good night, everybody.